So welcome everyone who's online. I'm sorry a little bit about commotion today. We had a hot water flood in the main classroom, adding to our usual start of the semester disorganization. Now, everybody, certainly the online people, have probably gotten emails from Whitney Thomas. And if you're not on Whitney's email list, you should email her. For the people who are on Columbia Courseworks, I sent an announcement to that effect. If you're not on Columbia Courseworks and you don't know Whitney's email address, I can get it to you after class. Because she'll be putting out most of the announcements for the class. The lectures are recorded, so we'll post them. The notes will be available. I have to get the Dropbox link set up, and Whitney will send everybody the Dropbox link so you can get the PowerPoints going forward. In addition to me, and if you don't know, I'm Art Palmer in the Department of Biochemistry and Molecular Biophysics at Columbia. The other instructors are Ann McDermott from the Chemistry Department and Hashima Hashimi, also from the Biochemistry Department. And Ann will give lectures on tensors, solid state NMR, and dynamics, and Hashim on applications to dynamics and also nucleic acids. There may be other guest lecturers along the way. That's still being worked out, but mostly you'll see the three of us. Usually on Wednesdays, we'll have a problem session after the initial lecture. That won't happen today. We may go a little longer today as a result, because obviously you haven't had time to do any problems. And I'll get the problem sets posted to the Dropbox link as well, or have Whitney just email the problems out. For the students who have to get a grade, there is usually a midterm and a final paper. We're having some discussions about whether we want to change that, but it won't change very much. So for right now, you can imagine there's a midterm and a final paper. I also should say it. Anish, are you online today?
Yes, I'm here.
So Anish in Ann's lab is also going to help out at various points through the course, a little bit to be determined, but with problem sessions, and also hopefully some additional modules in the course or simulations in the course. So you'll see him as well. That's all I can think of about logistics. I'm sure I've left things out, but we'll cover them as we go. Not what I wanted. So most of the course material is pulled from these two books, and certainly I hope most of the NMR labs have a copy of at least the first one, and if not, please get a copy for the lab, get your boss to get a copy for the lab. I earn about $1 per book, so you won't be making me all that wealthy. Anyhow, so today we start in the beginning. I mean, the main part of the course is going to revolve around the quantum mechanical mathematics underlying NMR. But we start from the beginning with the Bloch equations and the behavior just of a single spin 1/2 particle. And this is because ultimately, after we do a lot of quantum mechanics, we're going to try to get to a formalism that looks very much like the Bloch equations, except bigger dimensional matrices. So that will mean that the insights from the Bloch equations are going to stand us in good stead going forward anyhow. And the Bloch equations are 3x3 matrices, and that's about as complicated a matrix as you want to deal with by hand anyhow. And after that, mostly computer calculations. So that's where we'll start. And hopefully everyone online and in the room have at least collected a 1D NMR spectrum at some point. NMR is the best way to learn quantum mechanics because the NMR spectra show the quantum mechanics very directly. On the other hand, it's all very arcane if you've not actually ever collected a spectrum. So while the class itself doesn't have a practical aspect of working on the spectrometer, it's a good idea at various points if you haven't collected particular spectra to find some free time and collect some data. And actually, for people in the city, it's easy to come here and use one of the lower field machines if you need to. So this is the NMR spectrum of ubiquitin. A lot of the example spectra shown in the course on proteins anyway will be on ubiquitin. And of course, one of the first things you notice is there's dispersion in the spectrum. So the amides resonate a different position from the methyls, for example. And even within the amides, you can see there's substantial dispersion of different amide groups. So some of the dispersion comes from the difference in the chemical and magnetic environment of a hydrogen connected to a nitrogen in an amide as compared to a hydrogen connected to a carbon in a methyl group. And then within an individual chemical group, dispersion comes from the local magnetic interactions that come from secondary and tertiary structure. So of course, we're quite interested in secondary and tertiary structure in proteins from a structural standpoint, or changes due to changes in conformation. And we'll talk more about the magnetic interactions that lead to dispersion and chemical shifts. For a while, we'll just take them as a given. Here they are. A lot of the course, of course, is focused on dynamics, just because the three lecturers are interested in dynamics. And already you can see in the inset that the lines have different line widths or line shapes. And the line for isoleucine 61 gamma hydrogen is obviously much broader than it is for the leucine 50 delta. And you can start to see fine structure in the leucine 50 delta where there's splitting of the line into a doublet. The doublet, of course, comes from the J coupling, the scalar coupling. The difference in line widths has to do with the different motional properties of a methyl group that's spinning around quite rapidly and the line becomes narrow, versus the gamma 1 of isoleucine, which is primarily dominated just by overall tumbling rather than the fast rotation like a methyl group has. So one sees right from the beginning differences in line shape telling us there's different dynamics going on in different parts of the protein. And eventually what we want to get to is understanding pulse sequences like this, which have dozens, if not hundreds, of pulses and are moving magnetization around in complicated ways between different nuclei, primarily for solution NMR by the scalar coupling, or the nuclear overhauser effect, but in solids primarily by the direct dipole coupling. And one of the great results of NMR theory is eventually, hopefully, we'll be able to recognize that a complicated sequence like this is really composed of repeated, relatively simple building blocks, so that once one knows the building blocks, the sequences become much more intelligible. And as I said, we're interested in structure and dynamics. Here's the structure of ubiquitin, a ribbon diagram on the left, and an ensemble of structures on the right. And again, you can see right away in some places, like down here, this side chain, you can see there's mostly well ordering with one member of the ensemble pointing in a different direction, whereas the tail, C-terminus of ubiquitin, is just moving around. It's unrestrained by the experimental data, and we know from relaxation experiments it really is disordered. And just by way of introduction, here are two simple measures of motion in ubiquitin that will come up over and over again. The S squared is called the square of the generalized order parameter. It goes between 0 and 1, with 1 being rigid, and you see it's fairly high in secondary structure, and dips down in the loops in ubiquitin, or the tail here becomes even lower. That's depicted in the picture of an ellipsoid that tumbles in solution, that the order parameter is the amplitude of some motion. It has some time scale, and then there may be slower processes there denoted as REX that are larger jumps between conformations. And we tend to think at first order approximation, the molecule has overall tumbling, typically on a nanosecond time scale. For the size proteins we work on in NMR, they're fast, low amplitude motions characterized by an order parameter and a time scale that are perhaps picoseconds to nanosecond time scale, and then slower jump-like motions, more like motions over an activation barrier on microsecond to millisecond time scale called REX. And of course, the Hashim and Palmer labs make their livings measuring these motions and hoping that they're important for function. All right, let me try to, oh, you don't see what blocks my screen. So NMR exists because some nuclei have a property of spin. And when they have what's called the intrinsic spin, then they're NMR active, and we can do NMR. The spin is quantified by a quantum number that we call capital I, and it can be integer or half integer. For at least for solution NMR, almost all of the experiments are on half integer nuclei, with the exception of deuterium, which has spin equal to 1. And that's because half integer nuclei tend to have relatively narrow lines because they don't have a quadrupole moment. And the other nuclei, spin 1, spin 3 halves, etc., have quadrupole moments. That tends to broaden the lines a lot. Solid state life is much different, and particularly in inorganic chemistry, there's just a whole litany of nuclei that are used of all different sorts of spins. But for us, we'll talk predominantly about spin 1/2. I always find it interesting that spin comes from much more complicated phenomenology than charge. The charge of the proton is +1, and that's because the charge of the 3 quarks add up to +1. The spin comes from a complicated mix of the spins of the quarks and the spins of the gluons provide the strong force holding the quarks together. And it's still being worked out, I think, and might chime in what the exact percentage is that comes from the gluons versus the quarks, but a lot of it comes from the gluons, whereas the charge just comes from the quarks. Oh, we moved on somehow. Go back. So the nuclei have the spin, and they're then going to have a resonance frequency, as we'll see. And the resonance frequency depends on the size of the magnet and a proportionality constant called the magnetogyric ratio, gamma. And you can see it has units of reciprocal Tesla, reciprocal seconds, so that if the magnetic field is measured in Tesla, then the magnetic field times gamma gives a frequency with units of 1/seconds. So these are angular units, which we'll always call omega, as opposed to hertz, which we would get by then dividing by 2 pi. And when you're doing problems, you'll make lots of 2 pi errors in NMR, because one is always switching back between angular units and hertz. For us, or at least for me, gamma is just some number that was written down along with the 10 Commandments on stone. I don't know how you calculate gamma, quantum mechanically. Maybe Ann does, but these are just constants. You can see gamma can be positive or negative. It's famously negative for nitrogen, which can cause lots of confusion. And then the third important parameter is how much of the nucleus there is. Hydrogen 1 is great. It's nearly 100% abundant. But you can see, for example, carbon 13 is only 1% abundant. Carbon 12 is spin 0, so it's not active in an NMR experiment. So the naturally abundant carbon is visible to us. Similarly, nitrogen 15 has an abundance of 0.37%. It's very low abundance. Nitrogen 14 is the naturally abundant isotope, but it's spin 1 and has quite bad relaxation properties. So there's very little NMR done in biology of nitrogen 14. Jeffrey Bodenhausen does some from time to time, but it's just very difficult. So mostly one either has to work with natural abundance, in which case sensitivity is very low, or have ways of enriching in carbon 13 or nitrogen 15. And of course, a lot of the development starting in the late 1980s is better and better biochemical or synthetic ways of getting isotopes into biomolecules, so we overcome this natural abundance problem.
What about F19?
F19 is also spin 1/2 and close to 100% abundance, But of course, you have to have a way of getting the F19 in. So
Yeah.
I should extend the table because F19 has become very popular now
Yeah.
because there's lots of ways of getting an F19 into a protein. So I should add it into the table. Its frequency is quite close to hydrogen, so it's very high sensitivity, which is also nice. So the next few slides are just an introduction to the basic properties of spin in quantum mechanics. So because you have spin, there's angular momentum, and you all should know this from playing with tops when you were children. And if you didn't, you should complain to your parents that you didn't have enough tops. That would help you understand NMR decades later. And the angular momentum can be thought of as a vector with magnitude that's given by, shown here, h bar times the square root of I times I plus 1, where the italic I is the quantum number, the bold-faced I refers to the vector. And one of the results from quantum mechanics is that you can only specify simultaneously the magnitude of the angular momentum and one of its components. If it's a vector, it has 3 components. You can only specify one of them. By convention, that's the z component. And by convention, we define z in the laboratory frame as the axis of the magnet. So all of our magnets here are vertical bore magnets. So vertical is z in the laboratory frame. And the IZ component of the angular momentum is given by h bar times another quantum number, little m, which is called the magnetic quantum number because of its importance for NMR. And m has the property of going from minus I to plus I in steps of 1. So for spin 1/2, m can only be minus a half or plus a half. And that's quite convenient. The mathematics becomes simple because we only have 2 states of the z component of the magnetic of the angular momentum. So for spin 1/2, the quantum mechanical wave functions are called psi, and we can have a half or minus a half. And alpha is used to designate a half, so we don't have to keep writing a half all the time. We can just use the Greek letter alpha, and beta then is minus a half. So we have 2 wave functions. We have 2 quantum numbers for the z component, a half or minus a half. And then, because there's angular momentum, there's a magnetic moment. And this is where gamma, the magneto-gyric ratio, comes in. By the way, magneto-gyric ratio is the name given to the quantity by IUPAC. But many years ago, it was called the gyromagnetic ratio. So I'll accidentally switch back and forth. They mean the same thing. Magneto-gyric ratio and gyromagnetic ratio are both gamma. So the magnetic moment is proportional to the angular momentum, with gamma being the constant of proportionality. And then the magnetic moment along the z-axis is proportional to IZ. So it's gamma IZ or gamma H bar M. And if we go ask our physics friends, what's the energy of a magnetic moment in a magnetic field? They will tell you that the energy is minus mu dot B, where B is the magnetic field, and mu for us is gamma I, so I made a substitution. and the dot product is the usual dot product between two vectors. And if we talk about the Z component, then of course we just have substitute in for the Z component, and then the energy of a state with a given value of the magnetic quantum number just becomes minus m h bar gamma b in general. And if our static magnetic field for the NMR machine is called B naught, then we call the combination of minus gamma B naught the Larmor frequency. And if we plug in, for example, for the hydrogen, it's gamma and 11.74 Tesla for the magnet, then the absolute value of the Larmor frequency will be 2 pi times 500 megahertz, which is why a 500 megahertz NMR machine is called a 500 megahertz NMR spectrometer rather than 11.74 Tesla, as NMR people decided it was easier to remember the hydrogen Larmor frequency than Tesla's. The minus sign is an enormous headache for students. You just have to get used to the fact that there's a minus sign introduced. And my friend Dan Rowley says, you should not teach NMR starting with the hydrogen. You should start with the nitrogen, because then the minus sign of gamma cancels the minus sign in the Larmor frequency, and students don't have to worry about this. So if you want, you can just always think about nitrogen 15. So if M is plus or minus a half, then we have two different energies, depending on whether a given spin is in the alpha state or the beta state. And with our designations with this funny minus sign, alpha is the lower energy state if gamma is positive, because omega is negative in that case, and beta is the upper state. And there's then an energy difference between them. And if you all know, if there's an energy difference between two levels, we can do spectroscopy by introducing the right frequency of electromagnetic radiation. And you can see right away there, the energy difference between alpha and beta is, or its absolute value of the energy is h bar omega naught. So the frequency that we need is omega naught. So we have to turn on an electromagnetic frequency at omega naught to get any spectroscopy to happen. So this comes very simply, from these initial equations. It's also the case, right? If we have two energy levels that differ, then there's going to be a population difference between them. According to what equation? The Boltzmann equation. And the bigger the energy difference, the bigger the population difference, and the more sensitive the spectroscopy is going to be. Spectroscopy always will depend on the difference in populations between two states, and that tells you right away why we want bigger and bigger magnets. Omega naught is proportional to the size of the magnet. The bigger the magnet, the bigger the energy difference, the bigger the population difference. It also tells you why we like to work with nuclei with large gammas. The energy difference is proportional to gamma. So a large gamma gives a bigger energy difference. The ratio of gammas for nitrogen, the absolute value is about 10. So there's 10 times the energy difference for hydrogens rather than nitrogens. hydrogen is going to be way more sensitive a nucleus. So this is just the Boltzmann equation, and one can show, and I think you'll do it in the first problem, that for the size magnets that we have available to us, the exponential in the Boltzmann equation is very small, the argument to the exponential.
Hello.
The spin energy.
I'm wondering.
Oh, yes.
Yeah, I'm wondering if B naught in this particular Boltzmann equation can be the something as omega naught in the previous slide.
Right. So here where you see gamma B naught in this equation on the second line, minus gamma B naught would be omega naught from the previous slide.
Oh, shit.
So you can replace here the gamma B naught with minus omega naught.
Oh, okay. Thank you.
So these energies, our energy, magnetic energies, are very small compared to KT. So the exponentials can just be expanded to first order. And we find then that the population of a given state is just proportional to gamma B naught, or proportional to the Larmor frequency. So again, as I said, we want large magnetic fields and we want large gammas when we can. So we have, in general, M can go from minus I to plus I. And if we want to know the net magnetic moment of our sample, we just have to add up how many spins are in the alpha state, how many spins are in the beta state, and each one contributes a small magnetic moment along the z-axis. So we just have to add them up. So that's done here in the first equation. We can put in, again, the Boltzmann equation for the populations, but again, the exponentials can be expanded, and we have a funny summation to do. I don't know how to do it, but Mathematica does. So when we do the summation, we get an expression then for the net magnetic moment along Z of the sample. And you can see it depends on the quantum number I. It depends on gamma. It depends on B naught. So we mostly want to work with spin half. So we would plug in a half for the I. Again, you can see the magnetic moment is proportional to B naught and to gamma, or in this case, gamma is the negative. That's what we have to start with. We put the sample sitting on the lab bench. The Earth's magnetic field is very small, so there's essentially no population difference. You put the sample into the magnet, you wait a while, and a while will depend on relaxation rates that we'll come to, but eventually Boltzmann equilibrium is established under the new conditions of the big magnetic field. And this is, somehow this is on auto advance. This is how much magnetization you see on the z-axis. At equilibrium, at Boltzmann equilibrium, there's no transverse magnetization. Whatever fluctuations are happening in the transverse plane are averaged to zero. You know this because if there was transverse magnetization, we would put a coil of wire there and sell the resulting voltage to the power company. And since we can't do that, there can't be any transverse magnetization at Boltzmann equilibrium. There's a more more complicated quantum mechanical and statistical mechanical proof of that. But I like pointing out that NMR spectroscopists would be wealthy if we could just put a coil in the magnet and sell power to the power company. So then just for spin 1/2, here's what this looks like. The alpha state is slightly more populated than the beta state. And again, H bar gamma B naught over 4kT is a pretty small number for water in a 500 megahertz NMR spectrometer. The population difference is only about 10 to the minus 4. And so the population of the alpha state is something like a half plus 0.0004. And the population of the beta state is just a little bit less than a half. And that's why NMR is very sensitive. If you go to optical spectroscopy, where the energy differences are of order kilocalories or 100 kilocalories, the population of the upper state is essentially 0. So you have a huge population difference, and optical spectroscopy is way, way more sensitive than NMR. But again, this is why we want bigger and bigger magnets. So this picture just summarizes. We have a population difference between the upper state and the lower state. There's an energy gap. Absolute value would be H bar omega naught. And then we think we can do spectroscopy by applying the right frequency electromagnetic radiation. If we try to do an absorption experiment, we find out that's really painful because the population differences are so small that you very quickly equalize the populations of the upper and lower state, and then you can't get any more absorption. So in the early days, there were measurements done by absorption spectroscopy, but it's not how modern NMR is done. And modern NMR, we're going to generate transverse magnetization and record its evolution. And this isn't something you can do in your laboratory UV vis machine because it requires a coherent excitation source. And a UV vis machine generates photons that are incoherent with respect to each other. They have different phases. But we can generate RF frequency very easily that's phase coherent. The radio industry figured this out years ago. To do this with optical spectroscopy requires, very fancy phase coherent lasers. It's harder to get phase coherent photons at optical frequencies than it is at radio frequencies. So we have to change the picture, and we're going to ask, instead of thinking about absorption, we're going to think about rotation of this magnetic vector. So we have a vector that points in some direction. It bolts in equilibrium, but points along the z-axis. But we can go after.
I have a question.
Yes?
Since we know now that it's not appropriate to call an NMR spectrum, and it's not an absorption spectrum, can you then call it an emission spectrum? Or is that also mischaracterization?
Yeah, I think it's neither, but questions like that, I always defer to Anne. So if
Okay.
it's line, she can give her opinion. In the beginning of what's now called Fourier transform NMR, people worked on the theory a lot to show under what conditions would the Fourier transform NMR spectrum be identical to the absorption spectrum, or what was called then the slow passage spectrum. But since outside of a few very specialized applications, all NMR is essentially Fourier transform NMR, people don't care about that identity anymore. For us, the spectrum is the Fourier transform NMR, any other spectrum is sort of irrelevant.
Right. Thank you.
But we can ask Anne next time her feeling, because she did measure early in her career both absorption and emission lines by NMR.
Right, right. And a Fourier, the way in which like a pulse acquire Fourier transform experiment is characterized, at least in some books, I think, as stimulated emission, similar to what happens when you shoot a particle with a laser. So I just wanted to bring that up. Thank you.
We'll get Anne's opinion
Yes,
eventually. So if we go to our physicist friends and we say, I have a magnetic moment and a magnetic field, how do they evolve in time? And this is the equation. So the time dependence of the magnetic moment M evolves by the cross product of M with gamma times B, where B is the B field. And the cross product, remember, is you rotate one vector into the other with your right hand. Your thumb gives you a new direction. That's the rotation axis. And then you have the sine of the angle between M and B. So what this means is that the bulk magnetization is going to rotate around the instantaneous B field with constant angle between the two. And this is called precession, rotation at constant angle. And if you think back again, the tops when you were children, if you set the top spinning, it has angular momentum along its symmetry axis. And if it's spinning on the floor and it's not exactly straight up and down, you would notice a slow rotation of the top. There's the fast rotation of the disk in the top. That's uninteresting. That's just generating angular momentum. What's interesting is the slow rotational motion, and that's precession around the Earth's gravitational field, which looks to you like it's straight up and down. So the same thing happens here. The magnetic moment precesses at constant angle around the instantaneous field. If the instantaneous field changes, just the precession angle changes. Now, in reality, relaxation effects are going to interfere with this process. But for right now, we'll ignore relaxation. And we're just going to have precession. And the frequency is going to be minus gamma B naught. Now, if I think maybe next we get a picture. And Faraday's law says if we have a circuit, a coil of wire near our sample, the precessing magnetic moment or the rotation of this will change the flux through the metal, through the coil, and that will generate an electromotive force, and we can amplify that and display it on the computer screen, do whatever we want with it. So the idea is that if we have precessing magnetic moment, that will generate a current in the coil, in the probe, and we amplify that, and that's the NMR. So a very simple experiment. The only problem is we start with our magnetic field is on Z, and the bulk magnetic moment is on Z. And what's the cross product of two parallel vectors? 0. So at equilibrium, this doesn't work. At Boltzmann equilibrium, we can have plenty of magnetic moment, but we won't see any current in the coil. Like I said, we can't, otherwise we would sell it. So we have to somehow displace the magnetic moment away from the bulk magnetic field. And you could do this by rapidly tipping the magnet on its side, That's an experiment you can do once in your career before your boss fires you. So not recommended. You could rapidly move the sample out of one magnet into another magnet with a different orientation of the field. That's done in neutron spectroscopy, in fact, but that's also super expensive. So we will use a different trick. Anyhow, here's just a picture of what precession is. Red is the magnetic field, blue is the magnetic moment, and it's just the blue is just rotating at fixed angle. And if the red magnetic field changes its orientation, then the magnetic moment just keeps precessing, but there's a new angle. And if the strength changed, the precession frequency changed. So you can get very far in NMR just by saying the magnetic moment precesses around the instantaneous magnetic field. Spins aren't very smart. That's what they know how to do. They sense the instantaneous magnetic field and they just precess around it. This is what I've already said. So here's what our trick is going to be. We're going to turn on a second magnetic field. We call the static magnetic field B0. We're going to turn on a second magnetic field, orthogonal to the first one. And again, the spins aren't very smart. So what they sense is the vector sum of the two, the hypotenuse. So now our net magnetic field is displaced away from the z-axis by this vector sum. So the magnetic moment on z will start to precess around the new magnetic field and eventually won't be on z anymore. If it's not on z, it means there's some transverse component. And then we can measure the magnetic flux caused by rotation of that transverse component to get an NMR signal. So the idea would be turn on the second field, let the magnetization get away from the z-axis, turn off the second field, and now the magnetization will precess around B0, and we can measure then something in the foil. And one advantage of this is if we were doing an absorption experiment, we'd be turning B1 all the time and trying to measure absorption out of the field. But now we turn the B1 field off and then measure the consequences. So that's a much lower noise experiment. That's also why like fluorescence is so sensitive compared to absorption. You're measuring fluorescence, you can measure fluorescence in the absence of the excitation photons, so you don't have their noise complicating matters. Same thing here, we turn the B1 field off and we can measure what's a weak signal now in a low noise background. The only problem here is we can only turn on B1 fields of order kilohertz. So the vector sum between what's essentially micro Tesla B1 fields and Tesla static fields is the tilt away from the z-axis is very small. So we never get very far from the z-axis. And the trick is to modulate the field at the Larmor frequency. And maybe this will show the trick. Imagine you're down in Riverside Park at the swings and you want to push somebody on the swing. One way to push them is to give them a big push and off they go. Another way to do it is to give them a tiny push, run around the other side, and the moment they start to swing back, give them another tiny push, run back to the front, give them another tiny push just as they start to go the other way, And if you keep in synchrony, eventually they're swinging very widely because your little pushes are building up coherently. But you have to run at the natural frequency of the pendulum that they are, right? The swing of the pendulum. And if you do it wrong, then they just jitter and never get anywhere, and then the child gets mad at you. So we have to do the same thing. As the magnetization starts to process, we have to change our magnetic field in such a way that we're constantly pushing it a little further away from the z-axis. And maybe this will run. So here's the idea. Unfortunately, I switched the colors. Red is now the magnetization and blue is the magnetic field. So I'm going to start it tipped a little bit on one side. You'll see the precession, and then I'll switch it to the other side. And hopefully, my pointer go. You'll see the toggling. Even though I'm just moving the blue field back and forth the same small amount, you can see the red line gets further and further away from the z-axis, just as if I was pushing the swing in synchrony. Now, my simulation said I turn on a square wave so that I have the field along x and then along minus x, and then x minus x. That turns out to be both very hard to do electronically and unnecessary. It's good enough just to have a sine wave. And that sine wave has to be at the Larmor frequency or very close to the Larmor frequency. So our trick is to turn on a sine wave of some amplitude at the Larmor frequency and wait until the bulk magnetization has processed substantially away from the z-axis, and then we turn it off, and the magnetization vector will now process around the B0 field. And in fact, we can do this and get all of the magnetization into the transverse plane, what we call a 90-degree pulse, rotates the magnetization from the z-axis into the transverse plane, and then we'll get maximal signal in the coil. Or if we want to, we can do this longer and turn the magnetization upside down. When we rotate the magnetization by 90 degrees, there's no longer any Z magnetization. And that means the populations of alpha and beta are now equal to each other. In an absorption experiment, we would see nothing at all at this point. But here we see a huge signal because we've made this coherent state in the transverse plane. Similarly, if we turn the magnetization all the way upside down, we'll see no signal, but we've inverted the populations of the alpha and beta state. And you can't do that with the UV vis machine. You need a powerful phase coherent laser to do that.
Sorry, what do you mean by coherent states in the transverse plane?
So we'll come, just hold on that question. I'll show you what I mean eventually. And I shouldn't say coherent, I should say transverse coherence, just to avoid difficulties with quantum mechanicians. So that transverse magnetization reflects coherence, and I'll try to keep that separate from coherent. So we don't want to generate a square wave, and it turns out what we really need is a circularly polarized wave, because we're going to chase the processing magnetization, and generating a circularly polarized wave is in general too complicated. Sometimes people do it. So instead, we're going to use a coil that generates a linear polarized wave and then decompose it into two counter-rotating circularly polarized waves, one of which will do the NMR experiment, and the other one is just heating up the sample. That's the penalty we pay. Half of our power is doing nothing good for us, but it simplifies the construction of the NMR probe a lot. So that's what this factor of 2 is, because when I decompose into oppositely rotating, circularly polarized waves, only half the energy goes into one, half in the other, or half the amplitude. So that's the arithmetic. One wave is going the way I want, the other wave is going the wrong way, and I ignore the one that's going the wrong way. And I actually don't need to worry about which one is which. The experiment picks out the right one. So then the total magnetic field that I care about becomes the vector sum of the static field and this time-dependent field now that is circularly polarized in the right direction to follow the precessing magnetization. So then I'm back to this equation, and it's convenient then in NMR to switch into what's called the rotating frame. So our frequency differences between, say, different hydrogens in ubiquitin are going to be on the order of hertz to a few kilohertz. But the Larmor frequency is 500 megahertz. So we're talking about measuring very small changes in frequency. And this 500 megahertz is basically inconvenient. So we want to switch into a frame that's rotating at 500 megahertz. So we only see the small differences. So again, if you imagine going to Central Park to the carousel, and there's somebody walking on the carousel while it's going around, and you're standing on the sidewalk, you see the total sum of their motion, the motion of the carousel plus their motion. Whereas if you step onto the carousel, their motion becomes much simpler. You no longer see the motion of the carousel. So we want to do the same thing mathematically and work in a frame that's always rotating at a given frequency near 500 megahertz in this case. Usually the frequency we define that we're going to rotate at will be the frequency of the B1 field, which is something then that we can set. And then once we're in that frame, the frequencies that we'll measure are reduced frequencies that are the real frequency minus the frequency of the radio frequency field. And if we put the radio frequency field exactly to some resonance like water, it'll seem stationary to us in this rotating frame. And then something that has a higher frequency than water will look to us like it has a higher frequency, but we don't have to do 500.10003 minus 500.100035 when we're doing our math. We'll just be seeing the differences. So that's called the resonance offset, the real frequency minus the frequency of the RF field. And then otherwise, the equation looks exactly the same in the rotating frame as it does in the laboratory frame, which is very convenient. So here's again just the simulation. If I had a 1 megahertz NMR spectrometer and I turn on a pulse, the magnetization on Z starts to precess, and it starts to precess further and further away, just like in my simulation, but here you're seeing the three-dimensional projection, and eventually comes down into the transverse plane, and then I turn off the pulse. Now, suppose I shift into the rotating frame in which my signal is 0.2 megahertz offset from the rotating frame. And now you can see rotation again from the Z-axis down to the transverse plane, but it looks much slower because I'm running around at 0.8 megahertz, and I only see the much slower 0.2 megahertz. And if I go on resonance, I just see the magnetization appears to just rotate directly from the z-axis to the transverse plane. So the picture is much simpler in the rotating frame than it is in the laboratory frame. And as much as possible, except for relaxation theory, one's always going to be working in the rotating frame because the picture is so much simpler. So our magnetization vector is going to rotate around the instantaneous magnetic field as represented in the rotating frame in our theoretical picture. So here's the picture. The fact that we're in a rotating frame makes it look like we have a fictitious field along Z. Instead of the real B naught field along Z, we have a reduced B naught field that depends on the resonance offset divided by the gyromagnetic ratio. And if we're on resonance, omega is 0, and it looks like there is no B naught field anymore. There's only the B1 field left. And again, you're familiar with this. In amusement parks, there's this ride, sometimes called the rotor, where you're in a big cylinder with your back to the wall, and the cylinder rotates, and then the floor drops away, and you don't go anywhere. And that's because the centripetal force from the rotation is opposing gravity. And at the right rotation frequency, that exactly cancels gravity. So you just stay against the wall. You don't go anywhere. So this is the same idea. As we start to get into the rotate, as the rotating frame gets closer and closer to the Larmor frequency, the apparent magnetic field gets smaller and smaller. And if we're on resonance, the apparent magnetic field goes away. So here's the vector sum and just some equations that will come up over and over again. Then what's called the tilt angle theta is given by the trigonometry here of the effective field compared to the z-axis. So the tangent then is B1 over delta B naught. But if we work in frequency units most of the time, then that's the omega 1 field divided by the resonance offset is the tangent of the angle. And again, if we're on resonance, the angle becomes 90 degrees. And then the effective field, again in frequency units, is just the hypotenuse, the vector sum of the resonance offset, which we imagine along Z, and the B1 field in the transverse. There's then just some pictures. One important thing to note, of course, if we're on resonance, these rotations are very simple because, for example, if the B1 field is along the y-axis and the magnetization starts on Z, then a 90 degree rotation with a right-hand rule just brings the magnetization to the x-axis. We'll do lots of this. But if we're off resonance, the rotation is a precession around the instantaneous field, and it's much more complicated because it's around this cone. But in addition, the hypotenuse is always bigger than either of the two legs of the triangle. So when you go off resonance, you're rotating around the tilted field, but the rotation frequency is also larger. You can see this effect very easily on an NMR machine. Another way of putting this is, again, on resonance. If I have a 90 degree pulse, I can put the magnetization exactly on the x-axis. off resonance, the magnetization is not all going to end up in the transverse plane. Some will be left on Z, but even in the transverse plane, it's not going to be exactly on X. It's going to be rotated somewhere in the transverse plane. We call that a phase shift or a phase error. These things I've already said. And here's what I mean about generating coherence. So my sample, I can imagine as being a bunch of little blocks of spins. I don't like thinking about what one spin does. I imagine I have a bunch of little blocks of spins, each of which has a lock in it. And NMR sample has something like 10 to the 17 spins. So if I like, I can put 1 million spins in each box and still have plenty of boxes. So each of these little boxes has a little bit of magnetization pointing along the z-axis at Boltzmann equilibrium. And now when I turn on my B1 field, my pulse, and I say I want a pulse with X phase, what I mean is that the combination of the frequency generator, the amplifier, and the coil produce a field along the X direction everywhere in the sample. So the coil produces, or here a Y I've indicated, produces a field along the Y direction in the top of the sample, the middle of the sample, and the bottom of the sample. And this means that the sinusoidal wave has to be generated with the same initial phase everywhere in the sample, so that the pulse itself has phase coherence in space as it's generated into the sample. And that means each of these little blocks of magnetization sees a Y rotation by 90 degrees. Each of these end up on the x-axis, and they all add up to give a big x-axis signal, a big magnetization along the x-axis. If instead of an RF coil, I was doing this with, say, a hot piece of wire, like in the UV vis machine, the photons are being boiled off of individual hot atoms, and they all come off with random phases. And that would mean this top block perhaps sees an X pulse, and some other block sees a Y pulse, and another block sees a pulse with a phase of 135 degrees. And my billions of little blocks of magnetization would end up be pointing in all different directions in the transverse plane. And then when I try to measure a signal, an average sum up over the whole sample, I see nothing at all. And that's the difference. What I mean by coherence is that the pulse had phase coherence, and that phase coherence was transferred to a macroscopic coherence between the magnetizations in different parts of the sample.
So there is a difference between coherence and phase coherence.
Well, I'll use coherence to mean phase coherence, but I'll distinguish that from what a quantum mechanician would call a coherent state. Now, I think, again, it's always helpful to and back me up on theory details. I think for us, phase coherence and coherence mean the same thing. James Keeler had some experiments where he didn't want this to happen. So he took his probe and crushed the coil so that its carefully designed shape was messed up. And then we get RF pulses that didn't have phase coherence. And when it could end up with the state where the different little bits didn't add up, and you would get nothing. But again, I don't recommend that as a regular activity that you go in and crush the coil on the probes. But I think keeping this picture in mind, that what we mean is that the RF is phase coherent over the volume of the sample. So each little imaginary subblock sees the same pulse. And then we get a macroscopic adding up of the signals. When you buy a probe, it's usually spec'd as to how phase coherent it is. It's usually measured by how many times you can rotate the magnetization before it all gets dephased in the sample. So if different parts, imagine, suppose over the top and bottom, instead of getting exactly a 90-degree pulse, at the top you got 85 degrees and the bottom 105. As you did that, you would be scattering the signal, even if you're on resonance, in that case, you'd be scattering the signal in the XZ plane, over rotating and under rotating, and eventually you would blur everything out. So probes are spec, their phase coherence or amplitude coherence is usually spec by how many rotations you can do before you dephase. But that's related to how much dephasing there is in one rotation. So, how are we doing on time? So this is probably a good time to take a 5-minute break. And then we'll probably just go to 3 o'clock today, so everybody isn't too tired. But let's take a 5-minute break now. You can think about questions you have. But I assure you, if you think magnetization processes around the instantaneous field, and we have this picture of coherence coming from these little blocks of magnetization adding up together, you can get a long way in NMR. And I'll take advantage of a 5-minute break to drink my now cold coffee. We'll come back to that picture of the little blocks, by the way, when we come to relaxation theory, because that's also a phenomena that's going to dephase things from blocks to block.
Do TA and you or any of the professors have office hours, or is this the problem session is the office hour?
The problem session is kind of the formal office hours. But all three of us basically are never very far from email. So you can always email us, and we can either set up a Zoom or an additional meeting with questions.
I emailed you a lot of times, Professor.
What's that?
I emailed you a lot of times last, I think in my first year.
Did I ever answer? Oh, yeah. And I apologize. Usually the second email I answer, because the first email frequently, by the time I answer, people have already figured out their question. So I apologize. Whose group are you in?
Professor McDermott.
In that case, you should have told Dan to threaten me. Someone is taking advantage to stretch.
But I was wondering if I can ask a little question before the end of the break.
Sure.
Yeah, where you described, the previous slide where you talked about where you use small bus to represent net magnetization. Like, yeah, this one, yeah. This first one, can I see it as my sample that is sitting on a bench? But then I'm seeing that if this arrow, does it mean net magnetization of the
Right.
sample?
Right, so
Huh?
on the bench, each of those little arrows would be essentially zero pointing up and
Oh.
down because the magnetic field on the bench is so weak.
Okay.
And then,
So does
so
it mean that it will not have net magnetization?
there's no net, well, there's an infinitesimal amount of net magnetization on the bench coming from the Earth's magnetic field. But
Okay.
the Earth's magnetic field is many orders of magnitude smaller than an NMR spectrometer magnet. So if I've drawn those boxes, to be, say, a centimeter high, in each of the little vectors are a centimeter high in the magnet, on the lab bench, they're going to be a nanometer high. And they're just not going to add up to anything you can measure easily. I mean, there are people who do zero field NMR, but it's a different level of difficulty.
So this 90 is when it is put into into NMR spectrometer,
Yes.
and then the magnetization changes direction.
In the sitting on the lab bench, this tiny bit of magnetization from the Earth's magnetic field would be polarized along the Earth's magnetic field at that point, on the planet. So, of course, that varies from place to place on a planet, and people do measure that. But for us, that's essentially zero. And then when we put the sample into the magnet, a new Boltzmann equilibrium will be established where each of those little boxes has some polarization along the z direction. And then they all add up to give a macroscopic magnetization along the z direction.
So potentially they can align with the direction of the magnetic field of the instrument or against it.
So whether they're aligned with or against it depends on the sign of gamma, this geomagnetic ratio. So that's a peculiarity. So for nitrogen, the alignment is in the opposite direction from hydrogen. But that just swaps what we think of as alpha and beta states. It's not so, that part's not so important for us.
Okay. Okay, thank you so much.
Mm-hmm. Now, of course, if I, anticipating your question, had drawn further to the left the picture of the boxes sitting on the lab bench, there'd be essentially no magnetic vectors in them. And when you put the sample in the magnet, the magnetization doesn't appear instantaneously. Getting to Boltzmann equilibrium, if you're starting with equally populated states, spins have to flip from one state to the other to establish the new population. And that depends on a rate constant that's called R1 or a time constant called T1. And they're reciprocals of each other. And in the very beginning of NMR, Bloch suggested a very simple picture for relaxation. And one was that Z magnetization relaxed to Boltzmann equilibrium with a first order rate constant called R1, or its reciprocal is called T1. So when we put the sample in the magnet, to get to Boltzmann equilibrium is going to take some numbers of T1. So it's an exponential decay. So we might want to leave 5 times T1, or might expect that it takes 5 times T1 to get close to Boltzmann equilibrium. So that we're within e to the minus 5th of Boltzmann equilibrium, which is this, close to 0. On the other hand, if we're unlucky, I mean, most of your samples, the T1s are of an order of a few seconds or less. So by the time you put the sample in the magnet, tune the probe, have a cup of coffee, and get ready to do the experiment, you're at Boltzmann equilibrium. On the other hand, you could be unlucky. There are systems where the T1 is hours. And in that case, if you're in a big hurry to get your PhD done and you put the sample in the magnet and start measuring right away, you're not going to have any signal. And in fact, one of the first people to try to measure NMR picked a sample with a very, very long T1 and failed. As a result, he had no idea what the T1 was. And he just chose unwisely and later wrote a paper titled How I Almost Won the Nobel Prize. And then Bloch said that transverse magnetization will decay away also exponentially with a rate constant R2 or a time constant T2. And due to the nature of NMR, we'll see when we get to relaxation theory that R1 and R2 can be very different from each other. And from macromolecules, R1 can be much smaller than R2, or T1 can be much longer than T2. And this means, again, if we apply a 90-degree pulse, there's no more Z magnetization. The populations are equal. The populations aren't at Boltzmann equilibrium, but we have a lot of transverse magnetization. But if T2 is short, that transverse magnetization is going to decay away before there's any reestablishment of Boltzmann magnetization, if T1 is very long. So you can get to a state in NMR of biomolecules that seems very peculiar. All of your Z magnetization is gone, and all of the transverse magnetization is gone at the same time. Just the way it is. So relaxation in macromolecules anyway is not that the transverse magnetization rotates back to the Z axis. The transverse magnetization dephases, it goes away, and then on a different time scale, Z magnetization gets restored from the processes that can flip the spins between the alpha and beta states. When you get to relaxation theory, we'll spend a lot of time figuring out what are the molecular properties that give rise to R1 and R2. But for us right now, they're just something phenomenological. We can go measure them on the NMR machine and know what they are. So here's just an example of the pictures. If we invert Z magnetization, it will gradually recover with R1 back to Boltzmann equilibrium. And we can invert Z magnetization, we now know, by turning on the pulse long enough to get a 180-degree rotation. And then we can measure how much Z magnetization we have. So after some variable time, we apply a 90-degree pulse to measure how much Z magnetization there is. We apply a 180 and then immediately apply a 90, we're going to see a lot of upside down signal. If we wait a long time, we're going to see the positive signal again. And at some point, there's going to be a zero crossing where there is no Z magnetization and we'll see nothing. Transverse magnetization is just going to decay away until there's nothing left. And of course, that's very important to you because once all the transverse magnetization is decayed away, your experiment is over. There's nothing left to do. And then what are called the Bloch equations in the laboratory frame, we just take the precession equation and add in Bloch's relaxation equations. And we can expand out the cross product in terms of components by going back to our physics book. If we switch into the rotating frame, the differences are now we have the resonance offset representing rotations around Z, around the B naught field. And we have rotations around the omega-1 field. And whether theta here is the phase of the pulse. If they have phi. If phi is 0, we have an X pulse. If phi is pi over 2, we have a Y pulse. And on a modern spectrometer, we can set that to whatever we want. And you'll commonly see these written in the form of a matrix where we stack up the X, Y, and Z components of the magnetization. And then we have a matrix that governs evolution. So if we know where we're started, what our initial condition is, and we know the size of the resonance offsets, the phase, the B1 field, we can then calculate the evolution of the signal. If we turn off the B1 field, then we just have precession around B naught. So we just have resonance offset and then relaxation. Recovery back to Boltzmann equilibrium. And we, of course, can solve these or ask Mathematica to solve them or ask ChatGPT to solve them. So here are the equations, and they just say that Z magnetization just recovers back to Boltzmann equilibrium, and X and Y magnetization just represent rotation of a vector in the transverse plane with frequency omega and a damping constant of R2. So the picture's pretty simple, and we're going to measure these two components. The detector is set up, doesn't really have two coils. It's set up to look like it has two coils, one that measures the X component and one that measures the Y component. And then we can generate a spectrum from that signal. We need both because we switch into the rotating frame, and it could be that our resonance offsets are positive or negative. If we sit on the water for a protein, the amide hydrogens have higher frequency and the methyls are lower frequency. So in omegas, the methyls are negative and the amides are positive. And if we just measure one component, we can't tell positive from negative. And again, I used to give the analogy to setting your spark plug timing on a car, but that's meaningless to any of you. It's been known since time immemorial. If you have a rotating shaft in a motor and you want to measure both the rotation speed and the direction of rotation, you have to measure two orthogonal points. Because to know the sense of the rotation, you have to know if you pass here before here or here before here. So you need two orthogonal measurements to tell speed and sense of rotation. And that goes back to the beginning of motors. And that was always important when you were setting timing in your spark plugs. But not important anymore. And then if we say we're turning on a short pulse, short compared to the T1s and T2s, then we can ignore relaxation during the pulse. And I've just turned off the relaxation rates. And then we just have simple combination of rotations depending on the phase of the pulse. So there's two simple pictures free precession, no B1 field, or short pulses, no relaxation. And if we have to take everything into account, it's mostly a computer calculation at that point. If you go into the old literature, papers might have adopted a right-handed or a left-handed coordinate system. But pretty much since Richard Ernst wrote his book, everybody works with a right-handed coordinate system. But beware if you go into the early literature. So a right-handed coordinate system is written here. X, Y, and Z are defined so that if my fingers are on X and my thumb is on Z, the rotation goes to plus Y. So if I say I'm going to apply an X phase pulse, my thumb is along X, my fingers are wherever the magnetization is, and then I rotate. So Z goes to minus Y goes to minus Z goes to plus Y, and so on and so forth for the other rotations. So I've shown you the pictures and then the matrices for the rotations, but I spend a lot of time mentally just imagining the pictures. Of course, similarly, if we're off resonance, we have this more complicated situation rotating around the cone, but we'll ignore that for a while. If we're doing rotations around the Cartesian axes, then the picture is very simple. So for example, if I'm going to do a rotation around Y, starting with the magnetization on Z, the magnetization is going to rotate in the ZX plane. And if I turn the picture around, so the Y-axis is coming out of the board towards me, you can see there's an angle beta that I've rotated by. If I'm doing this, say with a pulse, an angle is always a frequency times the time. So beta would be omega 1 times t, the length of the pulse. Omega 1 would be the strength of the pulse in frequency units. And then you can see the trigonometry is very simple. After the pulse, there's going to be residual projection back onto the z-axis, and that will go as the cosine of the angle, and projection onto the new axis, in this case, on the plus x-axis by the sine. And it's always going to be the case. The original axis gets the cosine of the angle. The new axis gets the sine of the angle, sin of the angle. And then, for me, it's easiest to figure out, am I on the plus x or minus x axis just by doing the rotation with my hand, rather than to keep track of pluses and minuses, which I'm very bad at. So these kind of pictures we'll do over and over again. Precession is rotation around z. So x goes to y. I'll have cosine of an angle, cosine omega t on the x-axis, sine of omega t on the y-axis, so on and so forth. So we're going to do tons and tons of these, and you want to get very comfortable with right-hand rotations. Just more equations that are of more interest to you if you're writing a computer program. And then a problem some of you have done with me already is how do we treat the off resonance rotation, where we're not rotating around the Cartesian axis? And of course, if we're writing a computer program, we can just program this up. It's no problem. But to think about it conceptually, which is also, I think, useful for things we'll do later about how NMR in general works, is to imagine transforming to a new frame of reference where I know the answer. And most NMR problems are solved in this way. We try to go from whatever frame we're in where the problem looks complicated into a new frame where the problem looks simpler, solve the problem in the simpler frame, and then we can always transform back to the original frame if we need to. We've already done that with the rotating frame. In the lab frame, things look complicated because there's 500 megahertz rotation spinning around, and we simplify by going into the rotating frame, and we only see the residual hertz or kilohertz rotations. So here, we're going to do the same thing, and I know that Joshua knows how to solve the Rubik's Cube, so he knows that this is what I call the Rubik's Cube transformation. So we know how to do rotations along Cartesian axes. We're faced with a rotation that's not around a Cartesian axis. So we're going to transform everything to a new frame where the B effective field is on a Cartesian axis, then do the rotation, and then transform back to the original frame. So imagine our effective field, the vector sum, is oriented with a tilt angle from the z-axis of theta and a phase from the x-axis of phi. So the first thing I do is rotate around z by minus phi. And when I do that, the B1, the effective field, is now in the xz plane. So now I can do a rotation around y by minus z, or by minus theta, so that the effective field ends up on the z-axis. I could have done the rotation around y by pi over 2 minus theta and put the effective field on the x-axis. It doesn't matter to me. I just put it on a Cartesian axis. But of course, whatever rotations I applied to the effective field, I also had to apply to the magnetization. So the first rotation didn't do anything to the magnetization, but then the second rotation moved it out away from the z-axis. But now the effective field is on z. I just rotate by the angle alpha. Alpha is the effective field. Did I call it alpha? What did I call it? Looks like I forgot to call it anything. But if the rotation angle alpha was omega effective times the length of the pulse, I then rotate everything around z by that amount, and I can always do that by breaking the magnetization vector into its 3 components and rotating each component independently. And now I have to undo what I did. So now I have to rotate by around y by plus theta, and then around z by plus phi to get back to the original coordinate system. And that's guaranteed to work. So I went from a frame that was inconvenient to a frame that was convenient by a series of rotations. And then, having solved the problem in the convenient frame, I undo the transformations that got me there. In solid state NMR, if you're an AND group, you know that, for example, you start with, say, the chemical shift tensor in a molecule-based frame. Then you do a rotation to the crystallite frame, and then from the crystallite frame to the rotor frame, and then back again. So it's the same idea over and over in NMR. We're in a frame where we don't know how to, we're solving the problem looks inconvenient. and we try to find a frame where either we know how to solve the problem, or where at least the problem is much simpler, that we can maybe use perturbation theory or average Hamiltonian theory, etc., and then come out of that frame back to the original frame to see what the effect was. So this is the first example, I would say, of the general idea of frame transformations in NMR, which is why I like it. But it looks like I have to fix the figure somehow. Something's missing. And let's see where we are. Oh, we're doing fine. There's one thing about rotations is they don't commute with each other. So we're going to have to be careful throughout the course that we don't mix up which rotation comes first. The only exception is that infinitesimal rotations commute. So very tiny rotations commute with each other. And that's sometimes very useful in analyzing problems. So for example, if we're just a tiny bit off resonance, we might be able to commute some rotations that we wouldn't be able to do if we're way off resonance. And I think there's some examples of the math. So at the level of the block equations, for a single spin 1/2, we're done. We turn on a pulse, the magnetization gets rotated into the transverse plane. We turn off the pulse, magnetization processes. We measure the signal. It's a time domain signal. Humans don't like that, so we Fourier transform it to get a spectrum. And we can then measure the resonance frequencies. We can measure R1, we can measure R2. There's nothing else left in the block picture. So we're completely done with the theory at some level. Now, that said, we'll keep coming back to the block equations because, again, they're so tractable. And in modern NMR, you will see when you look in pulse sequences that there are many, many pulse elements that aren't turn on the field and turn it off again. So, for example, this is up in the upper left is the excitation profile if we just do a 180-degree pulse and look at inversion as a function of resonance offset. And we would like, usually the purpose of a 180-degree pulse is to actually invert magnetization. And you can see it's actually not very good. If we're on resonance, we get inversion, but as we move off resonance, the inversion gets to be very bad. And here, gamma B1 is a measure of the amplitude of the field. I would usually call that omega 1. And that means if you really want to get inversion, you need very strong fields. And you just can't do that at 900 megahertz. You're just going to burn out the amplifier or roast the sample. So over the years, various schemes have been developed that work a little better than just a simple 180-degree pulse. And the first one was just this sandwich of 90-degree X, 180-degree Y, 90-degree X. And I've done the calculation of the block equations for this. The calculations are just repeating our calculation over and over again, one pulse after the other. And you can see it's a little better here. There's pretty good inversion over a wider band than just a simple pulse. And here's another one, which is a little flatter, but at some additional cost, it's longer, so relaxation effects might worse. And here's another one. So we can come back to the block equations, at least in the absence of having to worry about relaxation or couplings, to look at these more complicated pulse sandwiches to understand how they work. These initial ones were thought up by Malcolm Levitt's intuition, but these days, oh, here's just some more counter plots showing how they work. These days, this is largely turned over to computers to optimize them. So, for example, which, this is probably what's called a snob pulse. And here's its excitation profile. And you can see it has the advantage of being a lot smoother than the ones I just showed you. And the bottom one is a Rebert pulse. And again, it's somewhat flatter. These look like continuous functions, but on the spectrometer, they're composed of a bunch of little skinny rectangles. So in fact, these profiles get calculated just as before. It's just you have a couple hundred rectangles. For each little rectangle, you calculate the evolution with the block equation, and that answer gets fed into the next rectangle. And you're not going to do that by hand. That's a job for the computer, but operationally, these apparently continuous functions are all broken into little rectangles by the spectrometer. And in fact, most of the time in the theory, we do the same thing. Break continuous time into very short time intervals and do the calculation piece by piece. And we can always make the time interval short enough for that to be okay. So then, right, here's the experiment. We wait a while for the magnetization to get near Boltzmann equilibrium, apply a pulse, record the signal. The signal is called the free induction decay. That's the current in the coil. Schematically, if we have a Y 90-degree pulse, the magnetization is rotated to the x-axis, the pulse is turned off, the magnetization processes in the XY plane, relaxes away with T2. We get a signal, we Fourier transform it to get a spectrum. That's called a one pulse experiment. That's as simple as it gets. Here's a picture looking down from the top. The magnetization is processing. We measure the X component. We measure the Y component. It's decaying away with its T2. There's the Fourier transform. The Fourier transform is a complex number. The spectrometer normally just shows you the real part. For a phase spectrum, the real part looks like the absorption line, and the imaginary part looks like this dispersive line. And if you've collected spectra, you know they frequently have some phase error, and that's because of delays. The real and imaginary magnetization that you think starts on X actually starts somewhere else. So that mixes the real and imaginary part, and then you phase to get them back to their absorptive line in the real channel, dispersive line in the imaginary channel. But you can ask the spectrometer to show you both if you want. It's there. And then these are the equations of the absorptive and dispersive line. There's just some math you can read. Definition of the Fourier transform, we'll come back to that. NMR spectrum. What else can we do just to finish? So I said we can measure T1 or R1. So now we have a 180-degree pulse. The magnetization is upside down. And now we're just going to have relaxation back towards Z magnetism. Boltzmann magnetization. But to measure it, we're going to wait a little while and then read out how much Z magnetization is left by turning the Z magnetization back to the transverse plane. Because we can't directly measure the Z magnetization. So the 180 turns the signal upside down. The signal then is going to relax according to its R1. We apply a 90-degree pulse to put it back into the transverse plane. And we record our signal. And here's the picture you saw before. Upside down, coming back to Boltzmann equilibrium. Here's an example for ubiquitin. The magnetization has been turned upside down. And wait a little while, you can see it's getting close to zero crossing. Here you can see that these spins have already passed zero. These aromatic spins are still upside down. They have different T1s. They're not all relaxing at the same rate. And you see that right away. And here we are getting back closer to Boltzmann equilibrium. I picked just this point, measured the intensities, did an equation that happens to have R1 of 0.9 per second, or T1 is about 1.1 seconds. So if I want to wait for Boltzmann equilibrium, I'm going to have to wait on the order of 5 seconds or so between scans. T2 measurement is a little more complicated because we have precession. And so now we make use of what's called the spin echo, perhaps the most famous discovery in all of NMR, made by Erwin Hahn when he was a graduate student. So there's things you can aspire to. So we're going to apply a 90-degree pulse to generate transverse magnetization. It's going to precess. And then the 180 is going to rotate the magnetization such that it will precess back to the starting axis at the end of the second delay. So all we'll see happen is the loss from T2, from relaxation. And we'll look at this, the spin echo many, many times going forward, but the 90-degree pulse put the magnetization on -y. During the first delay, we rotate from -y to +x, and the signal decays away due to R2. The 180 on Y does nothing to the Y magnetization, but it inverts the X magnetization. If I have my thumb along the Y-axis and I start with X magnetization, 180-degree rotation gives me back -X magnetization. And that's shown by the sign change. And then everybody rotates again. So I end up with 4 terms. And now I have to remember my high school trigonometry. And as you can see, 2 of the terms cancel and 2 of the other terms add up to be 1. The magnetization came back to where it started on the -y axis, except it's now smaller by a factor that depends on R2. So again, I record the spectra for different values of R2, and I look at the intensity decay. There's what it's going to look like. And here's just 2 points for ubiquitin out at the amide region. 2 millisecond delay, there was lots of intensity. 102 milliseconds, magnetization has decayed away. And just taking the ratio of those 2 gives an R2 of about 9 per second, or a T2 of about 100 milliseconds. And I think that's perfectly good place to start.
Can we go back to previous slide?
Yes,
The second to last step. What did we do there?
the 180.
Below that.
So then after the 180, I have some X magnetization. So during the second delay, that X magnetization is just going to process.
Oh, you're decomposing that magnetization again.
Yes. So that magnetization started out with the sine amplitude, factor that gets carried along, and then that will rotate, and the part that stays on X will pick up a cosine, and the part that goes to Y will pick up another sine factor. So I end up with 4 components, and then I just have to use trigonometry to sort them all out. So one thing you'll know by the end of the course is you'll know your trig sum and difference formulas. Any questions online before we stop for the day?
One of the books you gave me, sometimes I've seen that equation written with like -2 times R2T at the bottom. Where does the factor of 2 come?
Well, it would depend whether I called this delay T over 2 or T.
Oh, okay.
And when you look in the literature, people do it both ways. I do it both ways. So, yes.
And then this is just like a basic question, but for the Larmor precession frequency with that minus omega times gamma, just making sure if the gyromagnetic ratio is positive, that's corresponding to a clockwise.
So in our right-handed rule, that would be a that would be a clockwise rotation because it's negative.
Yeah.
So nitrogen would be a counterclockwise rotation.
Okay.
But as you can see, the difference between right-handed and left-handed at the end of the day is going to be, is your spectrum there are relatively few experiments where these differences are going to matter to you. I don't think we absolutely know which direction they rotate anyhow. Because we say we adopt a right-handed rule, we don't know what the spins have adopted necessarily for their rule. And what actually happens on the spectrometer, which side is really positive and which side is negative, is kind of complicated because of how the different frequencies are mixed. And Malcolm Levitt has a paper trying to work this out very carefully and deciding all the nitrogen spectra are displayed backwards anyhow. So most of the time I'm going to say when I'm calculating evolution, I think I have positive resonance offset, but that means I'm positive relative to my rotating frame. And of course, the rotating frame is what's either going at plus or minus, right? For hydrogen, it's going at plus 500 megahertz in a clockwise direction in my convention, whereas for nitrogen, it would be going 50 megahertz in a counterclockwise. But once I step onto it, I'm only measuring differences. And if I say my difference is positive, that's what I'm calling a right-handed rotation in the rotating frame. So the problem goes away a little bit in the rotating frame. But of course, the spectrometer itself is built in the laboratory frame. But I refer you to Malcolm's paper if you want to spend a lot of time trying to sort out what's happening in frequency synthesizers and amplifiers on a real spectrometer. And every time a new console gets developed by the vendors, these things might change. Famously, a 90-degree phase rotation for a pulse on a Varian machine was negative that of a Bruker machine. And no one really cared until TROSY happened, because then you needed a different phase cycle for TROSYs that on a Bruker machine than you did on a Varian, and everybody was confused for a while. Other questions? If not, we'll see you tomorrow. I'll try to get the Dropbox set up today so you can get these slides and the next lecture before tomorrow, and the recording posted. Thanks, everyone.
Thank you.
Thank you.
Thank you.